So in this lesson, we have a couple of objectives. We want to understand what happens when we form molecules and ionic compounds. How do we calculate the mass of those things? And you're going to find out. We're just going to use the numbers on the periodic table, and I'll show you how to do it. And we're going to be able to calculate how many atomic mass units a certain compound, like let's say carbon dioxide, would actually be. And so we're starting to get from the discussion of what's going on from a big picture down into getting a little bit more mathematical. Because remember, the goal of chemistry is to calculate things. We don't want to just talk about it. We want to say, in this chemical reaction, 43 grams of carbon dioxide is produced. We want to be able to calculate it. We want to be able to determine what happens, and we want to put numbers on it. So this is the first step in that direction. All right, so recall the concept of atomic mass, right? So we're going to get to molecular mass and formula mass for just a minute, but first I want to recall something. I want you to recall something that we've learned before because it ties into this lesson, right? You know, in chemistry, just like in most science classes and in math classes, if you can break down the barriers of the scary words, then everything is actually very understandable. So atomic mass sounds a little scary, but then you learn, well, it's just basically a measurement of how massive each of these atoms are. You start out with hydrogen, has 1 proton and 1 electron. And then you have helium, and then you find out that there's protons and also neutrons in the nucleus, and also electrons, but the electrons aren't very massive. They don't contribute too much. And you go up the periodic table, you can see these atomic masses are going up. That's 1.01, 4.00. You get down to something like mercury, with an atomic mass of 200.59. Mercury has a much more mass than these lighter atoms because they have more protons and neutrons in the nucleus. Remember, the mass of an atom is almost all governed by the amount of protons and the neutrons in the nucleus. It is true electrons have mass, but they're much, much less massive. They have charge, but they don't have very much mass. So most of the mass of these atoms are governed by the mass of the protons and the neutrons. Now, a couple things I want to talk about. I'm using this periodic table here. This periodic table has 2 digits after these decimals, most of the time anyway, to talk about the atomic mass. In whatever textbook you're using, or if you go onto the internet and find a random periodic table, you're going to see that the number of decimal places in different periodic tables can be different. You might see a table with only 2 decimal places or 3 decimal places, maybe even only 1 decimal place. So just use whatever you have and just know that your numbers may look slightly different than mine, but if you round them, then they're going to be the same thing. The more decimals you use, of course, the better your answer is going to be, because we can measure these atomic masses to very, very high degree of certainty nowadays, okay? All right, so we have to talk about the concept of atomic mass unit, right? Now, the atomic mass unit, if you remember back from the previous lecture that we talked about before, it is defined in terms of the element carbon. You see, you have to have some kind of standard. You have to have something somewhere, even a meter stick. There is a master meter stick in Europe that is in a museum, and it is the official length of a meter stick. There is a measurement for the official amount of mass of a kilogram. There is a measurement somewhere for the official length of 1 second of time. So for every unit we use in math or science, there's always an official standard that is the master standard for what it is. And so for atomic masses, because the atoms are so incredibly small, we pick one of these elements on the table, and a long time ago they picked carbon to be the official standard for the atomic mass unit. So carbon, if you remember, carbon-12, the most abundant form of carbon, has 6 protons, that's what the 6 here is, and also 6 neutrons. So what we say is that the definition of the atomic mass unit is defined in such a way that 12 atomic mass units is equal to exactly, and when I say equal to exactly, I mean it's defined as a standard to be equal to exactly 1 atom of the isotope, of the isotope carbon-12. Remember how we wrote these elements down? The element symbol is here. This is called the mass number, the number of protons plus neutrons. And you don't really need to write it, but you could write the number 6 here because carbon has 6 protons. But in the most abundant form of carbon, it has 6 protons, 6 neutrons. That means 12 for the mass number. Carbon-12 is the most abundant form of carbon. 6 protons, 6 neutrons. We define it to be exactly, and I don't mean we measure it, I'm saying we define it to be exactly 12 atomic mass units. 12 AMU. So another way of looking at it is saying, okay, if I could somehow take one of these atoms of carbon, isolate it by itself, it would be exactly 12 atomic mass units. So if I wanted to know what one atomic mass unit would be, then I would just take the mass of a carbon atom and divide it by 12. So if I could somehow take tweezers and take one carbon atom out and hold it, just one of them, that would be 12 atomic mass units. So by definition, one atomic mass unit is 1/12 of whatever a carbon atom's mass is, that carbon isotope. All right, so that's what an atomic mass unit is. Now I'm going to remind you of something else before we move on that you may or may not have remembered, but I want you to remember it. When you look at these numbers on the periodic table, notice carbon has an atomic number of 6, but the atomic mass, it does not say 12 atomic mass units. See, these numbers in atomic mass, that's atomic mass units. It doesn't say 12. On my chart, it says 12.01. Whatever chart you have might be something a little bit different, but it'll be not exactly 12. So why is it that this chart doesn't say 12 when I just told you right here that 12 atomic mass units is exactly equal to an atom of carbon? And that's because, remember, we have this idea of isotopes. You see, the elements on the table, they're defined by how many protons they have. Most atoms of carbon, well, all of them have 6 protons. Most of them have 6 neutrons. But you can have occasionally a rare carbon atom with 1 additional neutron in there. You can't have an extra proton because if you add an extra proton, then it becomes nitrogen. If you add another proton, it then becomes oxygen. So it still has to have 6 protons. And by default, it'll have 6 neutrons. But some of them, a very small fraction, will have an additional 1 or 2 neutrons. That's why you hear about carbon-12. That's the most abundant form of carbon. But there's also a carbon-14, which is not as stable. It's not stable because it has too many protons. But they do exist in nature, and they are stable for a certain period of time before they decay, right? And all of these atoms behave this way. Sulfur has an atomic number of 16, and it'll have a very common isotope of sulfur with a certain number of neutrons, but there'll be some very small fraction of sulfur atoms that might have 1 or 2 more or less neutrons. And when you add neutrons or subtract them from an atom, it changes the mass. So what I'm trying to tell you is that these atomic masses and atomic mass units that are written here, they are, in atomic mass units, the weighted average of all the isotopes of that element that exist in nature, right? I'll say that again. These numbers on the periodic table are already a weighted average of all the different masses of the isotopes that exist. So for instance, oxygen has some isotopes that are a little bit heavier as well. You know, selenium might have a couple of isotopes that are either a little bit heavier and a little bit lighter, but they're very rare. So when I say the weighted average, what we do is we look at the fractional abundance of each isotope and we multiply by the mass. So if, let's say, carbon-12 here with 12 atomic mass units is 99.99% abundant, then the 12 atomic mass units is multiplied by 0.99, let's say. But then maybe there's a slightly heavier version of carbon and it's very rare. So maybe it's only 0.001% abundant. So you multiply all that out, taking into account all the isotopes and their abundances, and add it all together, and the numbers that you get in this table are the weighted average of all the masses of all the isotopes for the elements that exist. And so that's why carbon says 12.01, because it's rolling in all the versions of carbon with a little bit more neutrons than the standard carbon-12. That's what I wanted to say. Now, back to the topic of atomic mass. Atomic mass, 12 atomic mass units, is exactly 1 atom of this isotope of carbon, carbon-12, 6 protons, 6 neutrons, okay? Now, let's talk about something related. If this is the case, then let's figure out what is the atomic mass, and we're going to get some molecular mass in just a second, atomic mass of hydrogen. Hydrogen. So we look on the table for hydrogen, and we see hydrogen is in this box right here, and the number here is 1.01. Now your table might have more digits. It probably does have more digits. That's okay. We know the masses of all of these elements very accurately, so you can treat all of those digits as exact. But for now, this table is rounded. So what I'm going to say is that the atomic mass of hydrogen is 1.01 atomic mass units. Remember, the definition of 12 of these atomic mass units is equal to 1 atom of carbon. So a mass of hydrogen is 1.01 atomic mass units. What is the atomic mass of oxygen, an oxygen atom? We go to the periodic table, we find oxygen, and we get 16.00. On your table, if you have more digits, it'll probably say 15.999 and then some other digits, because it's not quite 16, but this table is rounded to 16. So here I'll just put 16.00 atomic mass units. And notice, again, as I said, these numbers are already the weighted average of all the different isotopes of carbon of the element, in this case oxygen, that exist in nature. So this is called atomic mass because hydrogen is an atom. This is called atomic mass because oxygen is an atom. So we use the word atomic mass, we're just talking about the mass of an atom. Now, we know what the masses of the hydrogen and oxygen is. Now, what if we wanted to find the mass of something more complicated? Water, H2O. Well, water is not an atom, so we don't say atomic mass of water. I mean, you can, in free-flowing language, you could say that, but it would be wrong because atomic mass means mass of an atom. But water's not an atom, it's a collection of atoms. It's a molecule of atoms that are bonded together. So the better word is to call it the molecular mass, right? And so in the beginning, it can be confusing. Why do we say molecular mass instead of atomic mass? Well, atomic mass refers to atoms. Molecular mass refers to molecules. And water is a molecule. It is hydrogen, oxygen bonded together in a self-contained entity that can move as a unit, bounce off things, and so on. That's what the water molecule, is. And we've done, we've put these things up and showed you many times before. Water is in this bent configuration. We'll talk a lot more about that later. But what is the mass of this entity, of this water? Right? What would it be? Well, there's actually 2 hydrogen atoms here. So it is 1.01 for each one of them, but there's 2 of them. So we write that as 2 times 1.01. But then we have to add to it the mass of the oxygen, which we already wrote down, 16.00. These are all in atomic mass units. So when you multiply 2 times 1.01 and get the answer, and then you add to 16, you get 18.02. Right? Makes sense because this is like 2.02, right? And then you add to this and you get 18.02. What units are we dealing with? Atomic mass units. So what you can say with certainty is, if a carbon atom, a carbon-12, the most common form of carbon, has exactly 12 atomic mass units inside, or that's what the mass of it is, then the mass of water is a little bit more than that. So it is all relative, right? Because each of these individual atoms are so small, we cannot hold one of them in our hand. There's trillions of them that would fit on the tip of a pen, okay? So we can't hold one of them. But we can theoretically say, if we had one carbon atom, and if we had one water molecule, then the water molecule would have more mass. And because these numbers are kind of compared in atomic mass units on the same scale. So that is why we have to have a common frame of reference for measuring mass. Now this is called atomic mass unit. We call it atomic mass units, but the actual wording we say is molecular mass because water is a molecule. Now let's switch gears and let's say that we don't want to find the mass of water. Let's say we want to find the mass of sodium chloride. Mass of sodium chloride. Now we can figure it out. We're going to do it in just a second, but what would we actually call it? Well, we can't call it atomic mass because this is not an atom. It's multiple atoms together, but it's not a single atom. And we don't want to call it a molecular mass either because if you remember, sodium chloride is not a molecule. Sodium chloride, it's an ionic compound. We call it a formula unit, right? Remember, sodium is on the left-hand side of the table. It likes to lose an electron. Chlorine is on the right side of the table. So a metal plus a non-metal yield an ionic compound because the metal wants to lose an electron. The non-metal wants to gain that electron. So it loses the electron, it goes into to the chlorine atom, which gains it, and then you have opposite charges, positive and negative, and then opposites attract, and then they bond together. But they're not bonding together in a free-floating molecule because that's happening all around to all of the sodium and chlorine atoms, so it forms a three-dimensional crystal structure called a lattice, and we talked about that in the past. We don't call it a molecule because sodium chloride does not float around and bump around as a self-contained unit. It is in a three-dimensional structure. All ionic compounds are like that, right? Metal plus nonmetal, or metal plus polyatomic ion, like a nitrate or a sulfate, that would also form an ionic compound. So this is not a molecule, it's called a formula unit. So we call this a formula mass. Formula mass. This is where the word formula mass comes from. All right, now what's the mass of sodium? We look on the table, 22.99. So I put 22.99. There's only one of them, so I don't have to multiply or anything. And then I take a look at chlorine. Chlorine is over here. It's a heavier mass, right? Much heavier. It's got more protons and more neutrons. 35.45. 35.45. And so sodium chloride, when I take 22.99 plus 35.45, I get 58.44. And the unit here is atomic mass units. So again, you could compare these. That's why we have this. We could say, all right, sodium chloride as a formula unit of 1 atom of sodium and 1 atom of chlorine as a unit has a mass much, much higher than water and much, much higher than carbon. These two are kind of similar, but sodium chloride is much, much, much more massive, okay? Now, I want to remind you one last time before we move on that sodium chloride is not a free-floating thing connected together. It's in a crystal lattice, but in a simple ratio of simply 1 to 1. In other words, if I could put glasses on and look at table salt and microscopically zoom in and see all the atoms, then I would see a regular three-dimensional structure of sodium and chlorine, 1 sodium and 1 chlorine, and 1 sodium and 1 chlorine, and 1 sodium and 1 chlorine, and 1 sodium and 1 chlorine, three-dimensionally, 1 for 1, 1 for 1, 1 for 1, in a small ratio of 1 to 1. And that's why we write it like this. That's why we say sodium chloride, but just know it's a three-dimensional lattice. The fundamental formula unit has a mass of this. We call it a formula mass. So these different words mean something. Atomic mass, mass of an atom individually. Molecular mass, mass of any molecule, right? Which means covalently bonded to each other. Formula mass is metal plus nonmetal like this, and it forms a ionic compound. Now for the rest of the lesson, we're going to spend a little time calculating these masses. They're not hard. We're going to get very, very fast at it, but it's important because the very first step in solving real chemical reactions involves calculating these things. And we're going to learn about other topics in the future. We're going to learn about how to take these atomic mass units and turn them into grams, actual grams we can measure. We have to take a few steps before we get from here to there. For now, we're going to calculate these molecular masses and formula masses by using the numbers on the periodic table. All right, so let's take a look at problem number 1, or molecule number 1. So let's take a look at NO2. First of all, what is this? This is nitrogen and 2 oxygen atoms. Nitrogen, 2 oxygens, it's 2 nonmetals. So we know it's a covalently bonded guy. So we know it's a molecule. And the name of it would be nitrogen dioxide. Dioxide meaning 2 oxygens. Just like carbon dioxide, nitrogen dioxide would be this guy, right? So how would we figure out what the mass of this is? Well, we need to know the mass of nitrogen. And nitrogen, when you look here, 14.01 on my table, but when I solve these problems, I use different periodic table than the one on the board, so I'm actually going to use 14.007. This is a little bit more accurate to the real number. You don't have to use 3 decimal places, but a lot of times I will. And then we have 2 oxygen, so we have to take 2 and multiply it by whatever oxygen is, 16.00. But if you look on a more accurate table, 15.999. I'm going to use that number. You don't have to. You can certainly use 16. All right? So for NO2, so if you take 2 times 15.999, get that result, and add it to the 14.007, you'll get 46.005, and the units we're working in here are atomic mass units. And that is the mass. It's kind of a relative mass of nitrogen dioxide. Relative to what? Well, relative to what an atomic mass unit is, where carbon-12 is exactly defined to be 12 atomic mass units, so you can kind of get a relative feeling for how massive this is compared to something very common on Earth, essentially. All right, now we're going to do more of these, and you might get a little bored with doing them. There's 2 reasons why I'm doing them, and I want to give you those reasons so that you won't get so bored, because I want you to do them. I don't want you to skip through them, okay? Number 1, we're going to be doing more complex molecules and formula units, ionic compounds, okay? So the calculation will be a little more complex than this, but it'll be ultimately all the same concept, okay? And with that comes more complicated names. So even though we've already learned how to name things, I'm going to take the opportunity to tell you the names of a lot of these different compounds, so you're going to get a little bit more practice with naming stuff as we do this. That's number one. Number two, if you start using oxygen and nitrogen all the time, you're going to start to remember these numbers, okay? I don't remember if it's 14.007 necessarily, but I know that nitrogen's right around 14. And I know that oxygen is right around 16. So that can really save you, because you may not have to look them up in the table all the time if you're using them a lot. So I want to do a lot of them so that you get practice with it, get very, very comfortable with it. We get some practice seeing and naming more complicated compounds, and also maybe you'll start to remember some of these atomic masses. And so that's why we're doing it. All right, next item here. Here is a organic compound, C4H10, and I know we only have a very basic introduction to organic compounds, but if you remember, this is called a hydrocarbon, right? Because it is hydrogen and carbon with nothing else, right? And these things are named based on how many carbons there are. If there's one carbon, then it's called methane, methyl group. And then if there's two, it's called ethane, that's ethyl group. And if there's three of them, that's called propane, propyl group. And if there's four of them, that's butane. And so this thing is called butane. That's not really part of the problem, but this is what I'm trying to teach you as we go. So methyl, ethyl, propyl, butyl. Butyl means four carbons. Butane, the ane means there's single bonds everywhere. We'll talk about that stuff later, but this is butane, okay? What is the mass of a butane molecule? Notice that the carbon and the hydrogen, these are, as I mentioned in the past, anytime you have two nonmetals bonding together, we know it's a molecule. But hydrogen's a little weird. It's on the left side of the table, but when it bonds to these things over here, it behaves as a nonmetal. So even though it looks like it's a metal, hydrogen can sometimes act like a metal and sometimes act like a nonmetal. It can kind of have two personalities. But in general, when hydrogen is bonding with these things on the right, it's generally going to be a covalent bond, so it's going to be a molecule. So all of these organic compounds are molecules. They're literally clumps of 4 carbons and 10 hydrogens bonded together, and that's a free-floating thing that can bump in, and it acts as an independent entity there. So what would this be called, right? Well, for C4H10, right, what's it going to be? Well, there's 4 carbons. And what's the mass of carbon? Carbon is 12.01. Now, on my table, I'm going to use something a little bit more, with more decimals, 12.011. And then we're going to add that. We have 10 of these hydrogens. And hydrogen, again, is the lightest element, 1.01 there. And so it's going to be 10 times 1.008. So I'm just using a little more decimals there. You'll start to remember these after a while. Hydrogen is very close to 1. Carbon is very close to 12. And of course, carbon-12 isotope is exactly equal to 12. This is a weighted average of all the different flavors of carbon out there. So it's a little different than 12. That's because it's a weighted average. All right, so whenever you take 4 and multiply by 12.01, what do you get? You get 48,044. And when you take 10 times 1.008, you get 10.08. And so for C4H10, when you add these guys together, you get 58.124, and that's atomic mass units. All right, atomic mass units, 58.124 atomic mass units. All right, moving right along, we can speed up just a little bit. What about C6H12O6? I'm not expecting you to know what this is. We haven't learned this, okay? But I'm just telling you, this is glucose. You may have heard that, glucose monitoring, glucose measurement. It's a simple sugar. It's not table sugar. Table sugar is a slightly different than this. That's called sucrose. Glucose is, there are different kinds of sugars out there, I guess, is what I'm trying to say. And glucose is a simple sugar. Of course, it's in your body as well. 6 carbons, 12 hydrogens, and 6 oxygens. So how do we figure out what this thing is? Well, there's 6 carbons. We know carbon is close to 12. We just use carbon up here, so we can just write it down, 12.011. And then there's 12 of these hydrogens. And again, we just use hydrogen right here, so we can write that down again, 1.008. But then now we have oxygen. There's 6 of them, and we Actually, we just use oxygen up here as well, 15.999. So 15.999. All right. And so when we take and multiply this out, when we take 6 times 12.011, we get 066. And then we multiply this out, we get 12.096. And we multiply this out, we get 95.994. And so for C6H12O6, which is glucose, when you add these numbers together, you will get 180.156. What unit are we working in? Atomic mass unit. So you can see it's much, much, much more massive than water or any of these other things that we've talked about so far. Now, in the beginning, I'll do the multiplication, I'll write down the intermediate numbers, but I'll eventually stop doing that because I think you're capable of multiplying numbers and then adding them together. But in the beginning, we'll just get a little practice with it. All right, let's move along. Let's do a couple more on this board, and then I have another board over here to finish up. Let's take a look at CrNO3, okay? What is that? That's chromium nitrate. This is chromium atom. This is nitrate. It's actually chromium 3 nitrate. And we've learned this kind of thing before. The chromium and the NO3, the nitrate ion is a polyatomic ion with a charge of -1. The chromium is going to take on a charge of +3 in this case. And then when you do the crisscross, the 3 goes here and the 1 goes there. And that's why we are left with this. This is chromium nitrate. Now, how do we handle it? Well, there's only one chromium here. So that's easy. Chromium, when we go over here, chromium, I have 52.00, but the more accurate number is 51.996. And this is the chromium, okay? Now, what do we have? The NO3 has a 3 on the outside. So you have to multiply in, essentially there's a 1 here. So there's actually 3 nitrogens because there's 3 NO3s. So that means there's 3 nitrogens. And nitrogen, we know, is close to 14, 14.007. And so this is the nitrogen. There's 3 of them right here. Now, how many oxygens are there? If you cover this up, there's 3 of them because of this, but then there's 3 copies of the NO3 ion. So 3 times 3 is 9. There's actually 9 of these oxygens. 15.99. You'll remember that very, very quickly for oxygen. So this is the oxygen. So this is how you calculate it. You have 1 chromium, you have 3 nitrogens because of this. 3 times 1 is 3, and then 3 times 3 is 9 oxygens. All right, and so what you get is you have 51.996. The 3 times the 14 there, 0.007 for the nitrogen gives you 42.021. And then the 9 times the 15.999 gives you 143.991. And when you add all of these together, 51.996, 42.021, 143.991, you get 238 point, what did we get? 008. And that's atomic mass units. And that's an example of how you handle it when you have a polyatomic ion with parentheses like that. 238.008 for the mass of this is a formula mass, by the way. It's a formula mass because this is a metal. Chromium is clearly a metal, and a polyatomic ion, which is negative. So this forms an ionic compound formula unit. So this is called a formula mass, just like the sodium chloride was the formula mass. All right, we're making good progress. I think we're almost done, actually. We only have 2 more. Next, I want to find the mass of nitric acid. Now you might say, well, what is nitric acid? Well, you have to figure that out. Now you might remember it, but you might just memorize it because there's not that many acids and we often memorize them. But one thing you can say is you have nitric, and the ic is going to go to ate as a suffix. We learned that when we talked about acids. So this is nitrate. So another way of looking at it is like a nitrate acid, right? And what is a nitrate? A nitrate is NO3. That's a polyatomic ion with an overall negative charge. NO3, that's a nitrate. So the ic goes to the suffix of ate, nitrate acid, essentially. And acids have hydrogen in there, so hydrogen is involved. And in order to balance this, since this whole thing is a negative charge, the hydrogen has to have a positive charge. And when you do the crisscross, it's HNO3. 3 because the 1 goes here and the 1 goes there. HNO3, that's what nitric acid is. So you'll probably just remember it, but I wanted to go through the process to, help us out. So now that we've done this enough, we know hydrogen is very close to 1, and so we use the number 1.008 atomic mass units in the periodic table. Nitrogen is very, very close to 14. In fact, we're going to use 14.007 atomic mass units. 3 oxygens. Oxygen, we're going to use 15.999 because you could round up to 16 if you wish. All right, and so you have the 1.008, you have the 14.007, and then the 3 times this is going to give you 47.997. And so what you're going to get is, when you add the 1.008, the 14.007, the 47.997, you'll get 63.012 atomic mass units. And that's for HNO3. That's nitric acid. All right, only one more, and then we're going to call it a day for this lesson. Let's take a look at KMnO4. What is this? Well, the K is potassium, and then you have this manganese. Mn is manganese. If you're not sure about that, go look at the periodic table. Mn is manganese. But MnO4 is an ion that's called a permanganate ion. So this is potassium permanganate. Right? And if you're not sure about that, we could just quickly say, all right, well, potassium is here. Permanganate ion, if you look in a table of polyatomic ions, is the MnO4 as an ion. And that MnO4 as an ion has a charge of -1, and potassium has a charge of +1. If you look on the periodic table, you will see potassium wants to lose 1 single electron. And you will see this permanganate ion, MnO4, has an overall charge of -1. So when you do the crisscross, you get K subscript 1, MnO4, again, subscript 1 there. So how do we find the mass of this thing? Well, what's the mass of potassium? Mass of potassium works out to be 39.098. That's the potassium. Then we have to have the mass of this permanganate, 54.938. And this actually it's not the manganate, it's manganese. If you look at Mn, manganese, 54.94 is what it's rounded to here, and then 39.10 there. So this is 39.1, 54.9, you can see there. And how many oxygens do we have? We have 4 of these oxygens. We already know that, 15.999. We don't need to write down oxygen. We know that when we use it so much. And so whenever you take the number 4, multiply by this, get an answer, add this to it, add this to it, what you're going to get is 158.032, and what are we working in? Atomic mass units. And what would this be? This is a metal, potassium's a metal, and a polyatomic ion which has a negative charge, so they're ionically attracted to each other, so this is an ionic compound, so this is a formula unit, so this is called a formula mass. So basically, ionic compounds, we refer to it as formula mass, and molecules, which are nonmetals bonded together, we call it covalent bond, we call it molecular mass, right? So when we were doing these over here, with this is 2 nonmetals, that's a molecular mass. The hydrogen is acting as a nonmetal here, even though it's on the left side of the table. This is always a molecule, we call it molecular mass. We call this molecular mass. But whenever we have a metal, like potassium, either with a polyatomic ion or with a nonmetal, we call it an ionic compound, we call it a formula mass. So just getting practice with using the masses in the periodic table to calculate the overall mass of some sort of compound. I'd like you to practice all of these yourself. It's not hard, but you will have to do it for almost every single problem in chemistry. When we deal with reactions, almost always the first step is, what is the mass of that compound? And you're going to have to figure it out. So practice these, follow me on to the next lesson. We'll continue to build your skills with formula masses and molecular masses. Learn anything at mathandscience.com.